Hey everyone, Tim here. In this video, we're going to take a look at the wacky world of electromagnetic transient studies. And I love a good chart, and this one is particularly appealing since on the horizontal axis, it's logarithmic. Exciting, eh? So on the horizontal axis, we do have time in seconds, and you see that it varies from all the way from probably hours or maybe even days down to less than a microsecond, 10 to the negative seventh. And obviously what this is showing is some different phenomenon on the power system and the time frames that are needed in a software to study those particular phenomenon. And for example, over here in PowerFlow, we're looking at 10 to the third second, so that's about 1,000 seconds. But PowerFlow is pretty much a steady state type of study, as well as short circuit, that's also a steady state type of study. Moving over towards the left and going up a little bit, you will see transient stability, which we have just discussed, and transient stability anywhere from 0.1 seconds, which is about 6 cycles, up to 10 seconds or so. That's the time frame in which transient stability events happen and that they have to be studied. And then looking a little bit further to the left and up to the top, we see some phenomenon, lightning propagation and switching surges. Now, those two were the predominant use of electromagnetic transients until we started to see a lot more inverter-based resources on the system. And now that we are having to understand how inverter-based controls, how they really function, and we realize that they need to be studied down in this time frame, then electromagnetic transient software can also be used to study inverter-based controls. All right, so that's why we're talking about EMT studies and analysis in this video. An important point here is that EMT studies are also time-based simulation, and as long as you do them at a small enough time step, then you can model the power system at all frequencies, not just fundamental frequency of 60 hertz. And of course, we can contrast that, as we just did, with the phasor domain RMS simulations at a single frequency of 60 hertz, such as load flows and short circuit studies. And with a time-based simulation, you can model system dynamics. So EMT actually is based upon a solution of time-based differential equations. We won't go into those into too much detail, but there is one over on the right. And the time steps in a EMT study is typically 10 to 20 microseconds. And as we mentioned, you can model the behavior of power electronics such as solar PV inverters and storage inverters and other power electronic equipment that you see on the system. So at this point, you may be asking, why do we have to have EMT studies done as part of an interconnection study? And the answer is not just to keep geeky engineers employed, but there have been quite a few events on the bulk power system in the U.S. that were exacerbated, made worse by solar PV plants and to some degree wind plants as well. And two of these happened out in Odessa, Texas. In 2021, the solar PV plants in the Odessa area reduced the power output due to inverter level, feeder level tripping or control system behavior after a fault had occurred in the area. But the solar PV plants didn't reduce their power due to the fault. They reduced it subsequent to the fault, which is not an ideal situation. And then in 2022, in June, a similar event occurred in which about 1,700 megawatts of inverter-based resources from many different facilities, they also unexpectedly reduced their power output due to protection and controls at the site. So what NERC has been coming to the conclusion is that these types of events and all forms of tripping or abnormal performance can be modeled in EMT simulations and should be studied during the interconnection study process so that they can be identified before plants are put in service. However, these studies are not widely conducted. So NERC said there is a need for electromagnetic transient modeling requirements and accurate EMT models for all bulk power system, BPS, connected inverter-based resources. And FERC also has agreed with that, and not quite as strongly, but FERC said that for all interconnection studies that the interconnection customer should provide an EMT model if the transmission provider is performing EMT studies and that they request one. In March of 2023, NERC came out with a reliability guideline, and you can see the title of it here. So these are recommended requirements and verification practices. The guidelines say should. They do not say shall. So when it says should, that's a recommendation. Transmission Planning Organization should require EMT model requirement for all newly connected inverter-based resources to the bulk power system. And transmission plannings can still apply a screening to determine when EMT studies are necessary. Transmission owners can include modeling requirements in their standard interconnection agreements, and then generation owners should prepare for the need to provide EMT models that are high quality, validated, facility specific with documentation. In other words, not a bunch of junk, right? And then the generation owners should work closely with equipment manufacturers and consultants if needed. So those two parties, they do have a lot of expertise when it comes to EMT, both the inverter manufacturers, and there are a number of consultants out there that specialize in EMT studies. And then the models should be fully verified. I won't go into detail on this model. You see over on the left the traditional uses of EMT, and over on the right you see the use of EMT for inverter-based resource system studies, and you see instances in which it's more likely that an EMT study. EMTP, by the way, was the former terminology for EMT, but this is where EMT studies are going to really come into play. Integration into weak networks, meaning radial types of networks or networks that don't have a lot of generation connected into them. That's what weak means. High penetration regions of inverter-based resources. Think California, some parts of Texas, some parts of Minnesota. So places where frequency and voltage ride-through are required. And now that this is frequency and voltage ride-throughs are being required, so EMT is good for studying those. Control interactions, that's important. And that's both within a plant and between different plants. The stability of controls of inverters as well as the power plant controller, and then subsynchronous control interactions, particularly when generating stations may experience subsynchronous resonance between power electronics and synchronous machines. So now that you've heard the term, I won't be going into any more detail than that. This is a copy of a slide that comes from Electronics. They are very good at doing a lot of different studies. So if you have the need, look them up on the web. And I was attending a webinar and they presented this diagram. And this is a highly simplified EMT model of an inverter. And you see things such as reference values. And actually over on the left, you see the power plant controller. Now this is just the EMT model of the inverter over here on the right. You see measurements, and then you see some functions related to the inverter and how it performs its controls, all the way down to the firing controls on the right. And then in the bottom and in the yellow, you see a phase lock loop type of system. And then you see some protection that is also included in EMT studies. So these studies are very complex, and they are the domain of specialized power system control engineers. And actually, transmission-owning utilities, as well as ISO RTOs, they're going to have resources in-house, or they're going to be using outside consultants. Transmission providers and inverter manufacturers, as we mentioned, can provide help to interconnection customers, and larger developers and engineers may have staff to do EMT studies, but if they don't, then they're using consultants. And lastly, just to summarize, there have been documented system disturbances that were not predicted at time of interconnection, and that's why we have to do the EMT studies now, with Odessa in Texas, that being a primary example. Need to improve the accuracy and fidelity of engineering study for reliable IBR, inverter-based resource interconnections. That's the conclusions that NERC as well as FERC is coming to. EMT studies are capturing issues before equipment goes into service in places where transmission providers are using them. And, just as a fun fact, in the small print, you see if you are using a time step of 10 microseconds in a study, then EMT is calculating 600 steps per cycle. And, the power is 60 cycles per second. So multiply that by 60 and you'll get the number of steps per second. And that would be, I think it's 96,000 steps per second. That's pretty good. ISOs and transmission providers are already requesting the EMT models. For example, California ISO has been requesting them since 2018. And others include Southwest Power Pool. HECO is Hawaiian Electric. Very high densities of inverter-based resources in Hawaii. And then we've got ISO New England that actually requests them during the interconnection request window. And then we've got FERC Order 2023 that interconnection customers may need to supply the EMT model. And if applicable, the interconnection customer will provide that validated model if a transmission provider performs the EMT study as part of the interconnection process. So if a transmission provider does not do EMT studies, then the developers are off the hook, or the interconnection customers are off the hook and don't have to provide that validated EMT model. So that's all I have for this video. Leave me any questions on the discussion board, or I will see you at the next video.